Hello, everybody. So we're going to start. As we saw, Andrei today gave a good story at the beginning of his presentation, and all good talks start with a story. But I'm sorry to disappoint that this is not actually a talk. It's going to feel much more like a 1-hour lightning talk. So we're already out of time, and we have to continue. So about me, I'm from Bulgaria, some C++, only open source for the past few years, and my greatest achievement was DocTest, which is the fastest in terms of compile times testing framework for C++. And I'm very passionate about not wasting time. So has anyone ever seen this meme before? Yeah, it's pretty common in the C and C++ worlds, and it's our bane. So in this presentation, it's going to be online. It's online actually right now. You can follow along with the slides at this URL. We're going to start with the what and the why, and then we're going to continue with the how to actually improve build times in C++. So in reality, some projects, actually many projects compile for hours, and also not just the full rebuilds take that long, but also even incremental builds become longer and longer, and it just takes a lot of time to just see our smallest changes inside of the project. And for example, here's a case study about the build times of the Opera browser. In less than 4 years, their build time went from 15 minutes to more than 64, and they even incorporated a precompiled header at some point, and where we can see a dip at the middle, but it didn't help that much. So compile times are an issue for almost any big project. And this is a unique problem to C++. Other languages and people working in them, they just don't get it. How can a project compile for hours? So why do we want to reduce build times? Well, the first thing is money. Assuming you have a big salary, 80,000 years per year, if you're waiting 1 hour a day for builds, that's $10,000 per year for a developer. But actually, each developer costs a lot more to the company. He brings more value than what he's receiving, so let's multiply that by 3. And if there are 100 developers which are wasting time, that's actually $3 million for the company per year. And there are also other unquantifiable effects from long build times. They discourage refactoring and also experimentation, and you cannot put a price on that. Also, each time you have to build and you mentally switch to something else, that's a distraction, and then you have to take more time for you to get back into what you're doing. So the only logical thing is that any time spent on reducing build times is worthwhile, especially in big organizations. So C++ is built in the following way. First, there's the preprocessor. It takes a source file and it turns it into a translation unit by including all the headers transitively, also all the macros, and the conditional compilation goes off at that point. Then we turn to the compiler, which takes the translation unit and it turns it into an object file. That's comprised of parsing, optimizations, code generation. That's the compilation phase. And after that, the linker takes the different object files and other libraries, and it stitches them together into a final executable. So C++ compilation takes a lot of time, mainly because of the header approach for including headers. And C++ initially inherited this from C, and that led to the adoption of C++, so that's a big win, but also it's a big loss, because in time we built huge zero overhead abstractions in headers, and build times went down the drain. Also, the language itself is pretty complex, and there are multiple phases of translation, overloads, templates, it's not context independent, and the new standards, they add more and more complexity to the front end of the compilers. So yeah, all of our zero-cost abstractions end up in headers, and sometimes we're not using very good build systems and tooling setups, and sometimes even the projects themselves are structured badly. So you touch one thing, you have to rebuild everything. So if we take a C code base and we just compile it with a C++ compiler, we instantly get a 12% performance hit in terms of compile times, just because the front end is more complex because it's C++. And if we take a C++ 98 code base, and then we turn up the flags for +17, we can end up with up to 30% or even more heavier compile times, just because we're using the latest standard, even though the code is written in the old standard. And this, of course, varies wildly depending on the code you're profiling, but for a typical case with some templates like normal C++ 98 code, that's the case. And also, yeah, metaclasses, concepts, they're coming, and they will make the front ends of the compilers more complex. Why do includes suck? Well, they're textual, they're not symbolic. We cannot cache the results from the parsing of a header file, mainly because each time a header file is included, the meaning of the header file can be entirely different if something is defined above it. So the compiler has to reparse the headers and include all the includes each time a header is included. And also, many times dependencies and implementation details are leaked because in C++, private things aren't that private, actually. And also, the same code gets compiled many times. Suppose you have a big, heavy header file, which is included in 100 source files. So that means that header file is parsed and compiled 100 times. And the templates, if we're instantiating std vector in one source file and in another one, we're doing the same instantiation twice. And if we're instantiating the same template hundreds of times because of hundreds of source files, we're doing the same work again and again. And also, each time we define a function inside of a header file, so it's inline, so it has it's a weak symbol and stuff like that, it's actually more work for the compiler because it has to compile the function each time the header is included, and then the linker has more work to actually remove all the weak symbols except for one of them. So what happens if we just take a normal empty source file until we include a different header from the standard library, and we run the preprocessor? We sometimes end up with more than 1 megabyte of source code just after the preprocessing step. So that's like sometimes more than 50, 60, 100,000 lines of code for a simple header. And remember, our source file is empty. We haven't written anything inside of it. In the case of Boost, well, things are a bit bigger. So in the case of Boost geometry, for example, we get to almost 10 megabytes of source code just for including that single header, which includes like maybe hundreds of other headers transitively. So if we're compiling Boost geometry in 100 source files, we're actually compiling those same 10 megabytes of source code hundreds of times. And this is not a problem for Boost. The idea is that C++ has this issue. So we want to build these high-level abstractions, but the language has given us only includes. We need something better. So the first things for faster builds is we should be building in debug, at least in the development debug cycle. And it makes sense. But there are also different optimization levels. And for some companies, it's not viable to build in debug. For example, game companies, they cannot afford to actually build in debug because then the game will run with 1 FPS. So you can find some middle ground of where actually the thing is debuggable, but still not the optimizations are turned on. The next thing, so C++ has this philosophy to not pay for what you don't use. And if we have dead code, which is actually never called or never reached, there are a bunch of tools which can be used to analyze your source code, either statically or dynamically, to actually find pieces of code which are unreachable. And you can just remove those and speed up a little bit your compile times. So again, these slides are online, and all of these links and tools, you can check them out later on the web. Some other easy things are to remove unused source files and libraries from your build systems. You should scan the build logs for such cases. And each time you see a source file compiled more than once, that means you actually have to factor out into a separate static library, so it's compiled only once, and then you should link against it. And one reason people just include source files from somewhere else is because their build system is not flexible enough. So people are discouraged into doing things in the modular way, but actually that hurts our compile times. So we should also remove all the necessary includes, and we should also, forward declare things. So how do we find the necessary includes? There are a bunch of tools again. The most popular one of them is include what you use. It's Clang-based, so it should be pretty reliable. And some of these tools can help you with diagnosing not just what headers aren't needed, but what actually can be forward declared, so the header can then be removed. And we should also be striving for loose coupling. We shouldn't have a master header which is included everywhere and everything is inside of it, because then each time we touch one header, we actually have to rebuild everything. But that makes sense. So about declarations and definitions. So in this slide, we see that the full function is just declared. And the bar function and the method and the template function, they're all inline. So their bodies can be inside of the header file. That means they have there are weak symbols. They can be defined in multiple places, but then the linker will have to remove all of them except for one of the copies. So this isn't optimal because each time we include we include this header, these functions will be compiled again and again, and then the linker will have to do more work. And we should be trying to move all functions out of header files, at least their definitions, and do away only with a for declaration. And if we're concerned with link time optimizations, I mean, with inlining, we should use link time optimizations or unity builds. We'll get to those later. So for types, here we see that the full type is just forward declared, and then we're defining some other type. Inside of that type, we're using the bar type as a member, so we need the full definition of the bar type, and that's why we include the entire header for bar. But we can go by with just a forward declaration for the full type, because once we're using it as a pointer for the member of our new type, and also we're using it inside of a forward declaration. And notice that in the forward declaration of a method, I'm using the full type not by reference or as a pointer, but even by value. But since it's just a forward declaration of a function, we're not using it here, and we're not defining it here, then we don't actually need the full definition for the full type. This is actually a little less known by the C++ community, that you can actually go away with just a simple forward declaration in these cases, and you don't need the actual definition of full when you're doing forward declarations of functions which use the type even by value. But then, where we're implementing the interface source file in this case, since we're defining the actual full function, I mean the actual method, we need the definition of the full type, so that's why we include the full header as well. So again, we need forward declarations. We can go by with forward declaration each only when the types are used as a pointer or a reference, because a reference is actually a pointer underneath it. That's how the compilers implement the references. And also when they're used inside of forward declarations of functions. Third-party libraries. Well, it's a good idea to wrap heavy headers from third-party libraries in some custom, our own header file, so we don't expose the real header file. And for example, the STL provides the iOS FW header, which is with forward declarations for all the streams from the standard library. So you can just include that header and get only the forward declarations for all stream and other stream classes. So next up, the PIMPL idiom. It's known as compilation firewall, or a pointer to implementation, or a private implementation. And the idea is that we hold a pointer to the implementation inside of our classes. So here we see the widget class, and it has some public interface, but it also has as a field only one pointer, which is a pointer to an implementation. And here we see that the implementation class is just forward declared. It's not defined, so we can use a pointer to it. And where we implement the actual widget class, first we implement the implementation class, which was only forward declared previously, and then the public interface of the widget class, it just forward declares, for example, in the constructor, we allocate a new implementation. To the structure, we can just default it because we're using a unique pointer. And the public full method of the widget class, it just forwards the call to the implementation. So that's when you were using the PIMPL idiom, we don't need a full definition of the implementation inside of the header for the widget. So that's how actually the implementation is considered private. So there are some pros to this technique. Of course, it breaks the interface and implementation dependency, so you don't have to drag that much headers, and the compile times are much better. And also, it helps with preserving the ABI of your types. ABI is the application binary interface. So you can actually change the implementation. You can add more members to the implementation type, but the wrapper type will still be with the size of just a single pointer. So if the implementation changes and some DLL is rebuilt, you don't have to relink against the DLL. You can just work as before. So for example, many big softwares which need to provide a stable API with a stable ABI employ this PIMPL idiom. But there are also some problems. For example, it requires allocation, and there's also space overhead for the pointer. But we can use allocators for that. Also, there's this extra indirection of calls, but we can use link time optimizations. It's also more code to write, and there are many more gritty details about it, like const propagation and stuff like that. You should definitely check out that link if you're looking into employing the PIMPL idiom. We can also use abstract-based classes with virtual interfaces, and where we're implementing the factory functions which return different implementations of the base type. So yeah, we have factory functions which return pointers to the base type, but we're actually returning implementations which are derived from that base type. And again, this breaks the interface and implementation dependency somewhat because there's no data in the base class, but it also can be used for preserving the ABI. But actually, each time you change the virtual interface of the base class, you actually break the ABI. So the ABI is preserved only if you change if you add more data to the derived classes. But if you change the public interface, which is the virtual interface, then the ABI gets broken. But also there are, again, some problems, because, again, you have to allocate objects. They have to be on the heap. Again, there's an extra indirection of calls. It's more code to write. And people now have to work with pointers instead of values. And also, linked optimizations, they're a bit harder here to do anything about this. Devirtualization is a hard problem. A precompiled header is a header which you put many necessary things which are used across your project, and then you precompile that header just once, and you reuse the precompiled version of it in your entire project. So suppose you have 100 source files, and you always include stud vector. Well, it would make sense to put that header inside of a precompiled header, compile the stud vector templates just once, and then reuse that intermediate representation of the compiler again and again for the different source files. So what makes sense to go inside of a precompiled header? Headers that don't change, because the precompiled header has to be usually included in all of your sources in your project. So each time a header which is included in the precompiled header changes, you have to recompile everything again. So precompiled headers are mainly for reducing build times, and they're actually considered as a hack by many people, but they don't change the semantics of the language, not at all. And they're maybe the easiest to employ technique to speed up your builds. So suppose you include boost geometry in 100 source files. If you precompile that header just once and then reuse it, obviously you have like 10% of your original build time just because you've precompiled something huge. So precompiled headers are actually the easiest technique to employ in your build systems and in your projects to get drastic build time reduction. And this is, again, often disregarded by many professionals as it's a hack, it's ugly, but actually, if your project compiles for hours and then you cut it by half, that's good enough for me. So how do we use them? Most mainstream compilers support them. They can precompile headers and then reuse them. And many build systems support them out of the box. In the case of CMake, there are some external macros which can help with the maintenance of the actual precompilation of the headers. It's very easy. It's like one line of code in the build system. Unity builds. They're also known as amalgamated or jumbo or a single compilation unit. The idea is that we take a bunch of source files and we compile them inside of a single source file. We just include them and then we compile only the master Unity source file. We can actually split the many source files of our project not into a single Unity source file, but into multiple ones. For example, if we have 100 source files, we can split them in 10 Unity source files with 10 files in each. And the main benefits are, again, compile times, because suppose we were including boost geometry in all of our source files. Now, that header would be parsed and compiled only once, only for the first included CPP, which actually includes boost geometry. So that's probably the main reason why Unity builds are such a good technique to speed up your builds. And there's also less compiler invocation, because you have to compile less source files. And the same templates don't have to be reinstantiated again and again. For example, vector of integer, if you have to use it in core and widget, now it's instantiated in this Unity source file only once. So this is, again, a highly underrated technique, and it can actually speed up your builds by multiple times, like 5, 6, 7, 10, even 20 times, depending on the modularity of your code. And also, when you have less source files to compile, you have less object files to link, so the linker can actually do a bit faster. And also, this technique has been used in the game industry for a long time, and also some other big projects are now turning to Unity builds in addition to precompiled headers, for example, WebKit. So what are the pros? Of course, much faster build times, because we have to recompile the same headers fewer times, and then we have to reinstantiate the templates fewer times. And the best gains are, again, in the cases where we have short source files with heavy includes in them. It depends on how much abstraction we're using. And also, one other thing is that Unity builds are actually free link time optimizations. Link time optimizations are when you do cross-translation unit optimizations. So when you enable that flag for your release build, it actually makes the build much slower. With old link time optimization technology, it used to make builds like 4, 5, 10 times slower than the original build. But in the case of Unity builds, your builds are actually much faster, and you still have probably a single source file to compile. So all the functions see each other, and they can be more aggressively inlined and optimized. So this is free link time optimizations. And also, Unity builds are the most reliable way of catching one definition rule violations. Suppose somebody wrote a class in one source file, and then somebody, because he didn't want to factor it out in a header file and then include it, he decided to just copy-paste it in another source file. And then somebody decides that that class lives in only one of those places, and he changed the implementation of one of the implicitly inline methods. And now, what the linker does is, since these are weak symbols, it will actually remove from the final binary one of the methods which are defined here. So we'll end up calling always one of these two methods, and that will be not diagnosed. The program will compile and link successfully, but we'll be actually surprised from what we've done. And that's our fault, because we've actually violated the one definition rule. So Unity builds are the only and the single most effective tool of catching such violations. There are other sanitizer flags and compiler flags, but they don't work that reliably. And also, when you're using Unity builds, your code can be better, more clean. Like, you will be always using include guards for your headers, for example, and there will be less copy-paste like what I've shown above. But there are, of course, some problems. For example, minimal rebuilds, because if you put everything inside of one Unity source file, each time you touch one of your original source files, you have to recompile the whole thing again and again. But that can be actually solved with your build system setup. You can actually be able to remove a source file from unification and have it separate and compile it only it. One other thing is that if you put all of your source files into a single Unity source file, then there's nothing to parallelize, because now you have a single source file to compile. But again, you can split all of your source files into a couple of Unity source files. It doesn't have to be a single one. The other problem with Unity builds is that some C++ stops compiling. And that might be perhaps due to overload ambiguities or clashes of symbols in anonymous namespaces, or because of the preprocessor. But at least we got a compile time error, and we can just fix it and rename something or work around it. And the big problem with Unity builds are miscompilations, which are actually very rare. Nobody talks about them because maybe nobody has ever hit them, but it's possible to actually have your program to compile and link successfully, but the wrong thing can be getting called somewhere because of overload resolution. And our only line of defense for such miscompilations are good tests. But again, big projects are using Unity builds for the development lifecycle. They don't use them for release builds, but during development, it's okay. It's like a good trade-off if your builds are 10 times faster, or at least 3 times, 4 times faster. So how do we maintain Unity builds? We don't want to be manually including source files on our own, right? So for CMake, there are a few modules which help with that, and some build systems support Unity builds out of the box. Recently, Visual Studio added experimental support for them as well. So yeah, Unity builds are a hack. Not all valid C++ continues to compile, but they're just so worth it in our case for C++ that even Visual Studio has added experimental support for it. And all of these solutions, you can exclude certain files from unification, and you can also not have just a single Unity source file, but multiple ones, so you can have parallel builds. And there are other build systems which also support Unity builds. Inlining. So sometimes it might be a good idea to actually say explicitly, I don't want this function ever to be inlined. Because if a function is inlined 100 times for for a translation unit, that means that we'll have to do the inlining and compile the function a bunch of times. So we should also be careful with force inlining, where we actually tell the compiler, I want this to always be inlined. Sometimes it's not that good. And for compile times, of course it's not good, but sometimes we can mess up even our runtime if we inline aggressively. So that's a fuzzy topic. One thing people don't think about are destructors, because suppose you have a function with 10 exit points. That's 10 return statements. That's 10 places where the destructors get called. And if we have some type with a relatively small destructor, we can have its destructor inlined in 10 different places. And that's something we don't see. And that bloats our instruction cache. It can actually lead to runtime performance degradations. And also, of course, it takes much more time to compile. So that's something implicitly we don't see, actually, and we don't think that much about it. And whenever we have heavily repeated constructs, like, for example, an assert from a testing framework, like check this, check that, check that, check that, inside of a single test case, we don't need those things to be inlined, the checking function. And that's what my framework does extensively. It actually doesn't inline absolutely anything in the user code, and it's still the fastest even in runtime, not just compile times. So a little bit on templates. Suppose we have this template, and here the size method, it doesn't depend on the template type. But still, each time we instantiate this vector class, we also instantiate the size method for it, even though it doesn't depend on the type. What we can actually do in this case is factor it out inside of a base class, which is not templated. So we compile the size method only once, and then we inherit the base class from our new vector templated class. So now we won't have to instantiate a size member function for each time the whole template is instantiated. And now that it's out of a template, we can actually even remove it from the header file, and we can put it inside of a source file. So linkers, they can remove such identical functions, but first they have to instantiate them, and then they have to do more work to remove them. So it's much more work for your build times. So it makes sense to actually factor out template-independent code into base classes. And also, oh, I pressed something. I pressed end. Just a second. So yeah, if we're concerned about inlining, of course, we should be using link time optimizations or Unity builds. Of course, these are trade-offs, like how fast do you want your builds to be and how aggressive you want to be with your inlining. Next thing, extern templates. Suppose we have a header which defines an identity function, and then in some source file where we're using the vector class and the identity function, we can just say that we want the specific instantiations for the identity function, for example, in this case for int and float, to be externed. That means do not instantiate them in this translation unit, but we can still use them. And somewhere else, we'll have to explicitly instantiate the templates which have been externed elsewhere, so we don't have linker errors. So this was introduced in C++11, and actually some STL implementations even do this for stud basic string, because stud string is actually the template stud basic string of char. And it makes sense for us users to have that template externed, so we don't instantiate. We still parse it in our code when we include headers, but we don't want to instantiate it for the char type. And it's instantiated in the runtime. And yeah, that's about the external template. And if we want to also, I again pressed end. Sorry about that. Somehow, not my laptop. Okay, so we can also remove template function bodies out of headers, actually, and that's been possible since C++98. In this case, the identity function and the calculate method, they've been moved their bodies out of the header file and into a source file which implements them, but there we have to explicitly instantiate them for all the types which will be used with those templates. And now the user can just include the header and use those templates for the different types, but if a certain type hasn't been instantiated for somewhere explicitly, then we'll get link time error for that. But this is not a very advisable technique, but it still might make sense for some cases. If you know all the types a certain template will be instantiated in your entire project, you can actually instantiate them in a single source file where they're implemented and have the header with just the declarations of the template functions. So, last year, Odin Holmes gave a great talk at Code Dive in Poland, and there he summarized the rule of Shield, which is categorization of different template metaprogramming techniques and operations by their cost. So each time we look up a memoized type, which has already been instantiated, and we just reuse it again and again, for example, vector of integer a few times in a single translation unit, that's basically free. But each time we have to invoke the Sphene machinery, that's probably one of the heaviest operations with templates, and that's probably one of the biggest contributors to compile time degradation with heavy template use. Some other notes, of course, variadic templates, we should be a little bit careful with them. Recursive templates are bad, especially if they don't get memoized, so the different instantiations don't get reused. Also, recursive template arguments can be even worse because the type grows and grows and grows. And context per if can help a bit with compile times because we can use less Sphene now because of it. Tools, well, we can use the meta shell or the template tools to play around with templates and their instantiation process. We can profile with the template tool the time it takes to instantiate a different template and how much memory the compiler consumes and things like that. So these are really, really good tools. There's also for one of the IDEs such tool. Other good talks. Eddie gave a good talk last year at CFPCon where he talked how he optimized the compile times of thrift-generated code, where they were relying on Sphene, and they ended up using, again, press end, sorry, and they were using, instead of Sphene, at the end, type tagging to just leverage the overall resolution of C++. And he also talked about template in his talk, and the F-time report switch for the GCC compilers, which can give you a breakdown of where the compiler actually spent more time in the compilation phase. Also, Odin Holmes gives a lot of talks about template metaprogramming, so if you want to learn about how to write fast to compile and fast to execute metaprogramming algorithms, that's your talk, and that's the guy. More resources, of course, there's some books, some articles we can check out later on the slides, and I should add definitely much more slides and examples here. So, we want to diagnose compilations sometimes. And for GCC and Clang, there's the F-time report, as I said. And for Visual Studio, there's the BT flag, which will give, again, a breakdown of where more time was spent in the front end or the back end, or maybe more details. You should definitely check it out. And there's also this D2 CG summary flag, which was recently popularized. It was actually unknown, but available for quite some time. The curious thing about it is that it can give you a list of anomalistic compile time functions. So if you have a source file and some functions take like a long time to compile and they just get flagged as anomalies and they get reported for you to actually know which specific functions took so much time. So you can actually think about them. If we bloat our binaries with like a lot of templates and things like that, there's bloat and McBloat face and other tools for Windows to actually diagnose the binary, which sections are big and symbols and stuff like that. And yeah, a common culprit are usually templates. Build systems. Well, there are many, many build systems, of course. And there's some meta build systems, and some which are in between. Well, first of all, this is not a build system, because each time you have to recompile everything. The point of build systems is to do dependency tracking, so you can actually have minimal rebuilds, because you want to rebuild only the minimum amount of code when you touch something, the only things which are affected. So they help with managing scale, refactoring, restructuring, are hard without them, integrating tools, and they're not all equal, and also there are different trade-offs, of course. They're very, very different. And the more common ones, which are like more widely used, like Make or MS Build, which is behind Visual Studio, they have some they're not that optimal. And again, this is a huge topic, but here we're just going to focus really briefly about which ones are fastest. So we're not going to talk about different trade-offs, just what is fast. Of course, Ninja Fast Build and Incredibuild, they're the best in terms of parallelization. There are a few build systems I haven't looked into yet, like Bazel and Meson and one other, which are by Google, Facebook, and other such companies. So I suppose they're fast as well, but these ones are proven. For Make, we can make the parallel builds go parallel with -J. For MS Build, there's the MP flag, which we can use to compile source files within a project in parallel. But the MS Build scheduler for parallelization is not that great. For example, if we're building projects in parallel, and each of the projects is building its source files in parallel, we can end up with thread oversubscription. For example, 8x8, 64 threads, 64 compilers running at the same time. And again, we can use Ninja instead of MS Build for Visual Studio. There are some advancements, and there's this great article about diagnosing parallelization in builds by Bruce Dawson. You should definitely check it out on his blog. It's very, very in-depth on how you can actually profile and reason about it. And when we're using Unity builds, we should be careful about long polls, because we can end up with a single Unity source file, which actually takes a lot more to compile than the other Unity files. So we should be careful about that, and when we encounter such a thing, we should split it up in a few Unity source files. And also, modern link-time optimization technology is actually parallelizable, at least for Clang and I think Visual Studio as well. A little bit on meta-build systems. The idea is that we can describe a project canonically just once and then generate build files for many different specific build systems, hopefully with the addition to have IDE files, so build files for IDEs. And about CMake, because it's like the most widely used. We love to hate it, but it's the industry standard. To make CMake run faster, because some projects actually end up taking like 20, 30 seconds to run their CMake, we should be using modern CMake, which is target-based, like target include directories instead of include directories. There is also this project on GitHub which can speed up with compiler checks. And we might even consider building CMake on our own with link-time optimizations locally and native architecture, and with profile guided optimizations, which I won't have to talk about, which I won't have time to talk about in this lecture. Many times I've resorted to just diagnosing build parallelism using the simple task manager. But if you want to be more hardcore, you should definitely, again, check out that article by Bruce Dawson. And you might also switch to Incredibuild, because it's a paid tool, but it can be free if you're using it only on your machine, and you can still have access to the build monitor. And you can actually see very well which things are being built in parallel, where are the holes, what is the bottleneck. So in terms of winners, Fast Build is a very good build system. I haven't tried it yet, but it supports all of these things out of the box. Unity build, track compiled headers, caching, distributed builds, parallelization. It has a good scheduler, and it's a good approach. I mean, a good build system. Many game studios use it, actually. Ninja is also very fast. It's a Ninja. And Incredibuild. Tup is also probably one of the fastest possible things you can actually implement, but haven't tried it yet still. And these ones, I haven't tried them yet as well. So yeah, about PGO, the idea is that PGO is when you build your project once with instrumentation, then you run the instrumented binary on your training data, and you generate a profile, which the profile consists of which functions are actually called most often for this particular workload. And then, using that profile, you can recompile your program again, and then the optimizer will be able to better decide what to inline and what to not inline. So why am I talking about PGO and front-time performance in lecture about build times? Because you can actually bootstrap your compiler and to have it profile guided optimized for your exact source code, or at least on your machine. And it might make sense to have such bootstrap PGO optimized compilers on your built server machines. And there was this talk at CFPCon a few years ago by Matt, and he talks a little bit more length about this topic. A little bit about linking. That's it. Prefer dynamic linking over static linking. The linker does a lot less because it has to only work with the exported interface and doesn't have to actually work with the 100 megabyte object file or static library you gave it. So yeah, it's a big discussion, the different types of linking, but in terms of linking speed, no question about it. Even startup time of your program might be, no, let's not go there. So about symbol visibility. By default, when you want to link dynamically, you have to export symbols. And on Unix, all symbols are exported by default, which is the opposite to Windows. But you can actually make Unix behave like Windows using the visibility hidden flag. And in this case, Windows got it right. Specific explicit exports are much better instead of exporting absolutely every symbol. So if you're exporting only the minimum amount of set of interface you actually want to be exported, you have much better link times, you might have faster runtime, the load time of your program will be much faster, and your binaries will be smaller. And there are many, many more details on the visibility page of the documentation of GCC. And how do we actually explicitly annotate our API what to be exported, if we have to be explicit? Well, here in a platform and compiler agnostic way, we're defining symbol export and symbol import. And depending on if DLL exports is defined or not, my API will be either export or import. And then we define our API, in this case, a single free function called foo and the type called my class. And when we use this header, depending on if DLL exports is defined or not, we'll actually be either exporting or importing those symbols. So annotating explicitly APIs is not that hard. All you have to do is define some macro and then prefix a bunch of functions and be explicit about it. Linkers, well, on Unix machines, use GOAT instead of the default linker. It can also be multi-threaded. Also, part of the LLVM project is the LLD linker, which is getting more and more reliable, and it's even faster than GOAT. It's probably the fastest linker out there, and it's also multi-thread by default. It's a good idea also on Unix to split the debug information out of binaries, and of course your link times will vary depending on your code. And you can also build your linker yourself with profile guided optimizations and link time optimizations for itself if you're a fanatic. So linkers and link time optimization. Well, since recently, Clang has a scalable and incremental link time optimizer. Great. You should definitely check out that talk from CFPCon. There are some interesting articles about GCC, and for Visual Studio, they were actually putting a lot of work from Microsoft inside of their compiler, and there have been a lot of improvements in their linker and link time code generation technology as well. They also introduced a new flag called Debug FastLink, which is for a smaller, more compact version for PDB files. It makes link times much faster, and yeah, you should definitely check out these flags when you get the time with these slides later. Compiler caches. Well, the idea is that if we issue a compiler to compile something, and then we tell it to compile the same thing in the exact same way with the exact same flags and same compiler, we don't want to do that work again. So compiler wrappers or caches, the first time they compile your project, they save a hash for the preprocessed files you give it, along with the compilation flags which were used, and it maps those hashes to object files which are already compiled. So the next time you request to build the same source code with the same flags, the cache can just give you an object file instead of issuing the compiler to do it. So compiler caches, they work the best with full rebuilds, because if you actually change something, everything which depends on it will actually have to be rebuilt. So compiler caches are mostly useful for continuous integration builds, where you have a huge project, somebody pushes a change, that change affects only a small amount of the actual binary or the actual program, and the rest of the unaffected source code just gets, the object files for it get reused. So here we see that after we populate the cache, the second time we actually use a warm cache and we just trigger a rebuild, but we use the cache, it's almost instantaneous. It only has to, we only have to link the object files. So there are a few compiler caches for GCC and Clang, and fast build system supports caching out of the box. There are also distributed cloud storage, such caching services, and there's also the zapcc compiler, which is actually, it doesn't work as a compiler wrapper, but it's a Clang fork. It's an actual compiler which always sits in memory, and it caches, for example, template instantiations. And it was recently open sourced, and they report that WebKit can be built 2 to 5 times faster just by switching that compiler. Distributed builds. Well, the idea is that you can take advantage of the unused resources of your network. So your friends over there, they're using only 2 cores, and the other 6 cores are idle, and you can just tell them to help you out with a full rebuild of your project. So there's a scheduler which actually distributes work to different build machines, and those build machines can be either dedicated slaves which only work and only build their slaves, or other developer machines where actually somebody is working on. And it's all, again, you can set it up in different ways. And also, distributed builds, they work quite nicely together with caching, so you can actually combine those 2 techniques. And you should also watch out for network bottlenecks, like when the big object files start flying around because somebody else, a different daemon, gives you an already built object file, which is hundreds of megabytes of code, or at least a few megabytes. You can clock down the network, so you should be careful with that. And again, there are a few tools which do distributed compilation for C++ projects. The fast build system, it has distributed builds also. And that's it about them. Hardware, well, you need more cores and more RAM, and maybe SSDs. And if you have a lot of RAM, you can use RAM disks. So you can actually mount a virtual file system drive inside of your RAM if you have like more than 60 gigabytes of RAM. And a good idea is to mount the temp folders and where the output from the linker goes to the RAM disks. But again, the gains here won't be astronomical. You shouldn't expect like 2-fold faster link times and build times. A few percent, maybe 10, 20, depends. And again, that talk from Matt from a few years ago, it covers this topic as well. Physical design. Maybe sometimes we've messed up our design of our project in the first place. And we often don't think about the physical design, about how we actually structure files in our file system for our project. And also, many projects start out small, almost all of them, and they grow big, and some of them were just like an experimentation, but when you're big, it's already too late. If you don't think about the physical design from the start, or at least in the middle, when you still have time to change things, at one point it's too late. So we should be reasoning much more about components and modularity, of course, and the benefits are faster builds, we can more easily reason about the code and navigate in it, and we can refactor much more easily. There's this good article you should definitely check out. And also, if you're not familiar with John Lakos and his work from the past 2 decades, he's been a big speaker about physical design and large-scale software design. He's written a book, he has a few talks, and yeah, you should check him out about how to structure your code. And here's one other controversial article about this company called The Machinery, where they've made a limit, and a hard limit for themselves, to never include a header file inside of a header file. So some people go to extreme lengths to define a very, very strict physical design approach, just to keep compile times and modularity in check. So one might wonder, well, how do you actually work in such a code base where a header file cannot include another header file? But it turns out that they're building a game engine, and they have some experience with that. Their previous game engine was acquired by Autodesk, so they're actually pretty good software developers, and they know what they're doing. But again, what they're doing is a bit too much, maybe. But physical design is important, and people are experimenting. We should also be able to analyze our projects and their dependencies. So CMake can output a GraphVis file, which shows the dependencies of the different targets we have, and then we can visualize that text file with the GraphVis program, actually, and we can render a graph so we can check what links to what. Also, most of the tools from the unnecessary include slide from the beginning of the talk, they can also output some GraphVis file, or at least show you what depends on what, and so you can more easily reason about your project structure. And here's a visualization of such a graph. For example, in this case, we see that boost variant depends on a few other things. And it's much easier to see what depends on what when you actually have such a diagram, such a graph. So it's easier to analyze. Modules, well, they're coming. Yes, they'll save us. What about them? So the first proposal was 14 years ago. 14 years ago. It was dropped from C++11 because there were no implementations, actually, and there were still a lot of things to discuss. The first work on an implementation in compiler began in 2011, and in 2014, the push-push standardization continued with more proposals. And just a few days ago, the San Diego committee meeting ended, and modules will most probably enter C++ 20. A conservative estimate is C++ 23. But they will most probably enter 20. And here are the latest, again, papers and proposals you can check out if you want to know the cutting-edge idea about modules. What was the motivation behind them? Well, compile times, one of them. And the other thing is that preprocessor includes, it led to leaking symbols and implementation details, name clashes, tooling was hard, and there are many workarounds like include guards, which are why. And also, the order of includes matters. Sometimes a header depends on another header, and it's not actually included, or a header breaks after another header, and it's very messy. And also, with modules, things will be much more dry. We won't repeat ourselves. There will be much less for declarations, and we also won't have to split our code in headers and sources for the declarations and definitions. So in Visual Studio 2017, here is a simple module which we export called M1. And we export the getStrings function. Then we import that module, we use it, and it's great. We have to compile it like that from the command line because still there's almost no support from build systems for modules. And one of the reasons is that different compilers implement modules in a different way because there's still no standard. And they're experimenting. So yeah, this is how we use modules right now through the command line. How do they work? Well, inside of binary module interfaces, which are files, okay, so we define a module inside of module interface units. There we decide how to name the module and what to export. And when we compile interface units, we produce binary module interface files, BMIs, which are binary blobs. And they're like an internal representation for the compiler for the different symbols which have been exported. And unlike precompiled headers, modules can be composed, and you're explicit about what gets exported, which is good. So the current state is that big companies are pushing for modules, and we have implementations in the major compilers. The future is not clear, well, it's sort of clear now. They will most probably go in C++ 20. And when they're standardized, we won't get huge gains immediately. Because Build systems still don't support them. It turns out to be a really hard problem to support modules, and only Build 2 so far supports them. And also, even when we have all the tooling available, which actually works with modules, and build systems have them, they have to be adopted by software, and people have to update their tool chains, and they have to make changes to their source code, and they have to deal with third parties which don't want to upgrade. And also, there's this mantra: if it ain't broke, don't fix it. So we'll be dealing with legacy for a long time. So even though modules are coming, and they will obsolete things like precompiled headers and the PIMPL idiom to a large extent, they can still make sense, those techniques, because modules aren't here yet. And a little bit more on them. Well, a bunch of talks and a bunch of articles you should definitely check out later. The next steps. You should consider runtime compilation, actually, so you don't have to restart your entire application. And there are many different ways to approach it. It's been possible for the past 20 years for C and C++. It's nothing new, but it's sometimes hard to set up. And there are many ways to do it, and you can check them out on that link. You should also improve your source checkouts, your tests. You should use my testing framework because it compiles so fast, and that's the theme of the day. Also, you can parallelize tests in C-test, just like in make with -j. And that's it. Any questions? Well, there's one question over there. Is there a microphone?
Thanks. So you mentioned moving template functions out of headers, so the definition. That's not recommended. Why is that?
Well, why it's not recommended?
Yeah.
Well, it's not flexible, because if you move the definitions of the template functions out, you have to instantiate where they're defined for all the types which will be used for the entire project. So you have to know that. You cannot ship a library like that. So if you decide that that template will be used for only integer and float and some other type, and you know that for a fact, then it's okay. But usually it's not generic if it's constrained like that. So it's not.
No.
Yeah.
The case you mentioned was exactly the case I was thinking about, of trying out. So.
Okay. Any other questions? There's one over there.
So thank you. There was a lot of information.
Yeah, it's a lot.
Are you aware of any open source projects that employ a lot, or maybe all of the techniques you talked about, that could serve as a good example?
I can't think of such right now, but probably the best things you can employ are like precompiled headers, maybe Unity builds, maybe cleaning up your headers and dependencies. Examples for such projects, I'm not sure. You can check out my library, how it deals with some of these techniques, like only for declarations and no inlining, for example. But you should definitely experiment, and maybe some of these techniques are actually in conflict with one another. So it doesn't make sense to employ absolutely all of them. And some of them are also don't give that much gains. So you should experiment.
Yeah, thank you.
So I guess our time is up. Thanks again.